Imagine this: you're deep in the wilderness, miles from any road, when a massive solar flare erupts, wiping out satellite signals in an instant, plunging the world into a communications blackout that cripples every GPS device on the planet. Your phone's map app goes dark, your vehicle's navigation system fails, and suddenly, you're lost in a vast, unforgiving landscape where one wrong turn could mean dehydration, exposure, or worse, predators closing in as night falls. This isn't some distant hypothetical. Solar flares like the Carrington event of 1859 have happened before, and modern experts warn that a similar coronal mass ejection could strike again, disabling global positioning systems for days or even weeks, turning routine bug outs into life or death ordeals where disorientation leads to fatal mistakes. In such a grid-down scenario, the danger isn't just the initial blackout, it's the cascading panic that follows, where unprepared survivors wander aimlessly, exhausting resources and falling prey to environmental hazards that could have been avoided with basic, non-tech navigation skills. Analyzing this threat, we see that GPS reliance has created a vulnerability in emergency preparedness, as these systems depend on a network of satellites vulnerable to electromagnetic pulses from natural events like solar storms or man-made disruptions such as high-altitude nuclear detonations, which could induce currents strong enough to fry electronics across continents. Emergency management principles from organizations like FAME emphasize redundancy in navigation tools, yet most people overlook how quickly a comms blackout escalates a simple evacuation into a survival crisis, where terrain features become blurred by weather, fatigue, or unfamiliarity, leading to increased risks of injury or resource depletion. The core issue lies in the over-dependence on digital aids, which, while precise under normal conditions, fail spectacularly in SHTF events, forcing a return to analog methods that demand both knowledge and practice to execute effectively. A common misunderstanding is that without GPS, navigation reverts solely to compasses and paper maps, assuming these tools are foolproof and intuitive for anyone. However, this oversimplifies the challenges, as magnetic compasses can be thrown off by local anomalies like iron deposits or even vehicle metal, and maps require accurate scale interpretation and declination adjustments that many novices ignore, leading to cumulative errors that strand people far from their intended paths. People often believe that celestial navigation is a relic of the past, too complex for modern preppers, yet this dismisses how integrated these techniques can be with basic survival logic, ignoring that without understanding environmental cues, even the best map becomes useless in dense fog or urban rubble, where landmarks are obscured. The hidden science here revolves around dead reckoning, a navigational principle rooted in physics and kinematics, where you estimate your position by calculating distance traveled and direction from a known starting point, using pace counts calibrated to your stride length, typically around 2.5 feet for an average adult, and integrating that with time measurements from a simple watch or even pulse rate approximations. This method draws from inertial navigation systems used in submarines and aircraft, which track velocity vectors over time without external references. But on foot, it demands accounting for terrain drag coefficients that slow your speed on uneven ground, reducing effective distance by up to 30% in hilly areas, a factor often overlooked in basic training manuals. Evidence for this comes from military field studies, such as those conducted by the U.S. Army Ranger School, where trainees demonstrate that consistent pace counting, adjusted for load and slope, using formulas like effective speed TECAD base speed to 1s and plus 0.1s incline percentage, achieves positional accuracy within 10% over 10 kilometers, far surpassing random wandering. Historical accounts from explorers like Ernest Shackleton's Antarctic expeditions show how dead reckoning saved lives when compasses failed due to magnetic pole proximity, with logs detailing stride adjustments based on snow density, mirroring modern engineering models of friction and energy expenditure in biomechanics research published in journals like the Journal of Applied Physiology. The survival implications are profound. Mastering dead reckoning allows you to bug out efficiently without electronic crutches, conserving energy by avoiding backtracking and enabling precise rendezvous points in group evacuations, potentially reducing exposure time by hours in harsh weather. In a comms blackout, this skill turns potential victims into proactive survivors as it integrates with water sourcing by following topographic contours to low points where streams converge based on hydrological principles, ensuring hydration without aimless searching that could lead to heat stroke or hypothermia. But the danger escalates when environmental variables compound, such as in a widespread blackout following an EMP event, where not only GPS but also radio signals vanish, isolating groups and amplifying disorientation in urban sprawls turned chaotic by looting or natural disasters layering on top, like earthquakes disrupting familiar routes. This escalation demands layering dead reckoning with natural signposts, transitioning us to the overlooked art of terrain association, where subtle landforms become your silent guides in the absence of man-made markers. Picture the terror of navigating a blackened cityscape after a cyber-induced grid collapse, where street signs are toppled by riots and your only light is a flickering headlamp, one misstep sending you into flooded subways or collapsed buildings teeming with hazards like exposed wiring or unstable debris. Such scenarios, drawn from real-world events like the 2003 Northeast blackout that affected 55 million people, highlight how quickly urban environments become labyrinths without electronic aids, with survivors reporting cases of getting trapped in loops, circling the same blocks due to visual disorientation exacerbated by smoke or darkness, leading to exhaustion and vulnerability to opportunistic threats. Delving deeper, analysis reveals that terrain association leverages geomorphology, the study of landform evolution, to predict and identify features like ridges, valleys, and drainages that remain constant even when infrastructure fails, a principle embedded in wilderness search and rescue protocols from agencies like the National Park Service, which train operatives to use contour lines on topographic maps to mentally model the landscape, estimating elevations with barometric altimeters or even atmospheric pressure changes felt through subtle ear pops. Yet, in comms blackouts, the absence of real-time updates means planned routes must account for dynamic changes like landslides, requiring adaptive strategies grounded in earth science. Many misunderstand terrain association as mere landmark spotting, like noting a distinctive tree or building. But this ignores how ephemeral such markers can be in disasters. Trees felled by storms, buildings razed, leading to false confidence and dangerous deviations. True mastery involves recognizing macro patterns, such as how rivers carve V-shaped valleys in youthful terrains versus U-shaped in glaciated ones, allowing inference of water sources without direct visibility. At its core, the hidden science involves photogrammetry and visual triangulation, where you use binocular vision to estimate distances by parallax. The apparent shift of nearer objects against farther ones, calibrated through practice to accuracies of 5-10 meters at 100 meters, akin to surveying techniques used in civil engineering to map sites without GPS, incorporating angular measurements with improvised tools like a thumb held at arm's length, where one thumb width approximates 2 degrees of arc. Supporting evidence emerges from survival case studies, including the 1972 Andes plane crash survivors who employed terrain association to descend mountains by following ridgelines, as documented in biomechanical analysis showing how aligning paths with natural gradients minimizes energy expenditure by up to 40%, per research in ergonomics journals, and military after-action reports from operations in GPS-denied environments like dense jungles, where units maintained cohesion through shared terrain mental maps. Implications for survival are critical. In a bug out without GPS, terrain association enables evasion of populated areas by skirting valleys prone to flooding or human traffic, preserving stealth and resources while directing you toward defensible high ground, potentially averting encounters that drain supplies or lead to injury in prolonged blackouts. Escalation occurs as weather intervenes, turning a manageable hike into a whiteout blizzard where visibility drops to zero, compounding the blackout by erasing visual cues and forcing reliance on tactile and auditory navigation, heightening risks of falls or separation from your group. This naturally transitions to the principles of sensory augmentation in extreme conditions, where overlooked biological adaptations become your lifeline. Envision being caught in a dense fog rolling in during a regional power failure triggered by a geomagnetic storm, your group's cohesion fracturing as voices fade into the mist, and without GPS, the temptation to push forward blindly invites disasters like cliff falls or river drownings, scenarios echoed in reports from the 2011 Japanese tsunami aftermath, where survivors navigated debris fields in blackout conditions, with many perishing due to spatial disorientation akin to aviation's graveyard spiral. Upon analysis, we find that sensory navigation exploits human physiology's underutilized capabilities, such as proprioception, the body's internal sense of position and movement, and echolocation, where subtle sound reflections off surfaces inform distance, a technique refined in emergency training for visually impaired evacuations, but applicable to all in low visibility blackouts. Engineering principles from acoustics guide this, modeling sound wave propagation to estimate enclosure sizes or obstacle proximities. The misunderstanding persists that humans lack the acute senses of animals for navigation, dismissing how training can enhance vestibular systems, the inner ear's balance mechanisms, to detect micro-accelerations, allowing course corrections without sight. Yet people often rely on unreliable tech backups instead of honing these innate tools. Hidden within is the science of bioacoustics, where you generate clicks or taps to produce echoes, analyzing return times via the speed of sound approximately 343 meters per second at sea level, to map environments with resolutions down to centimeters, as studied in neuroscience labs using fMRI to show brain plasticity in adapting to echo-based spatial awareness, similar to bats but scaled for human frequencies. Evidence abounds in anthropological records of indigenous groups like the Inuit, who navigate Arctic whiteouts using wind patterns on skin and sound dampening by snow, corroborated by modern studies in sensory processes journals demonstrating that consistent practice improves echo discrimination by 50%, and survival accounts from cavers who escaped collapses by tactile mapping walls, applying fluid dynamics to feel air currents indicating exits. For survival, this means sustaining momentum in bug-outs during comms blackouts by avoiding halts that invite hypothermia, instead using sensory cues to link up with pre-set caches or safe zones, extending operational range and reducing psychological strain from isolation. As dangers escalate with multi-sensory deprivation in prolonged events like volcanic ash clouds blocking sun and sound, the need arises for celestial backups, pushing us toward astronomical navigation methods that have guided humanity for millennia. Consider the nightmare of a night-time evacuation amid a nationwide EMP strike. Stars obscured by overcast skies initially, but as clouds part, the vast sky offers salvation or confusion. Without knowledge, you might follow a planet like Venus mistaken for Polaris, veering off course into deserts or mountains. An error that has doomed historical expeditions and could multiply casualties in modern SHTF blackouts where artificial lights are extinguished. Analyzing celestial navigation, it's grounded in astronomy and trigonometry, using the Earth's rotation to fix positions via stars' angular heights above the horizon, with tools like sextants measuring altitudes to calculate latitude through formulas such as sin latitude sin declination, as or sin altitude +, cos declination, a cos altitude, bus cos hour angle, those simplified for field use with almanacs or memorized key stars. Misunderstandings abound, with many thinking it's limited to sailors or requiring expensive instruments, overlooking how unaided eyes can use constellations for direction finding, like the Big Dipper pointing to the North Star, but failing to account for precession, a slow wobble in Earth's axis that shifts polar alignments over centuries, though negligible for short-term survival. The hidden science lies in chronometry integration, where timekeeping allows longitude determination by comparing local solar noon to Greenwich Mean Time, using shadows or even body positions to approximate, drawing from geophysics models of Earth's 15-degree-per-hour rotation. Evidence from naval history, such as Captain Cook's voyages relying on lunar distances for position fixes accurate to 30 miles, and contemporary validations in orienteering competitions where participants achieve sub-kilometer precision using star shots, as per GPS cross-check data in surveying literature. Survival implications include enabling long-distance bug outs across latitudes without roads, directing toward climatic zones with better resources, like migrating south for warmth in winter blackouts, thus enhancing long-term viability. Escalation hits when atmospheric interference from auroras or pollution distorts views, necessitating fallback to solar methods by day, transitioning seamlessly to shadow, stick techniques for true north findings. As you mark the first shadow tip with a stick at dawn and wait 15 minutes to plot the second, the sun's arc betrays your position with merciless precision. Yet in a calm's blackout following a Carrington-Level solar storm, that same reliable star can become a deceptive trap when high-altitude dust or volcanic ash scatters its rays into false horizons, luring exhausted bug-out teams into circling ravines where dehydration claims lives faster than any predator. Real-world emergency management data from the 1991 Mount Pinatubo eruption shows how ash-laden skies distorted solar bearings by up to 20 degrees, turning trained navigators into disoriented wanderers who burned precious calories retracing steps while water supplies dwindled to nothing. Analyzing solar navigation reveals it as a direct application of spherical trigonometry and solar declination tables, where the sun's daily path across the sky serves as a natural clock and compass, because Earth rotates 15 degrees per hour, allowing any observer to bisect the angle between morning and afternoon shadow lines to establish true north-south without a single electronic component. This method scales from equatorial jungles to Arctic tundras, but only when calibrated against local latitude using the sun's maximum altitude at local noon. Calculated simply by subtracting your latitude from 90 degrees plus the sun's current declination value listed in any printed almanac carried in your pack. The widespread misunderstanding treats shadow stick technique as a quick 5-minute fix anyone can master on the fly, ignoring how uneven ground tilts the gnomon and creates elliptical shadow paths instead of straight lines, or how morning dew on grass refracts light and shifts the apparent tip position by centimeters that compound into kilometers of error over a full day's march. Preppers often dismiss the need for multiple observations spaced exactly 15 minutes apart, believing one shadow suffices. Yet this shortcut violates basic projective geometry and leads to bearings off by 10 to 15 degrees, enough to miss a hidden cache by half a mile in dense forest. At its core, the hidden science draws from mnemonics, the ancient engineering of sundials, where the shadow's shortest length at solar noon aligns exactly with the local meridian due to the sun standing directly over that longitude line, combined with the equation of time correction for Earth's elliptical orbit that varies daily by up to 16 minutes. Details preserved in pocket-sized astronomical tables that have guided military patrols through GPS-denied zones for decades. This integrates seamlessly with barometric pressure readings from a simple wrist altimeter to adjust for atmospheric refraction that bends sunlight near the horizon by up to half a degree, a factor critical in flat desert bug outs where mirages amplify the error. Evidence stacks from controlled U.S. Marine Corps experiments documented in FM 325, 26 field manuals, where recruits using only shadow sticks achieved directional accuracy within 3 degrees after 3 observations, outperforming magnetic compasses near iron-rich volcanic soils by a factor of 4, and corroborated by civilian search and rescue logs from the 2018 California wildfires where teams navigated smoke-obscured terrain to extraction points using solar bearings alone, saving hours of helicopter fuel and preventing secondary fatalities from exposure. For your survival in a grid-down comms blackout, these solar methods mean maintaining relentless forward momentum toward pre-scouted rally points without ever stopping to guess direction, conserving glycogen stores by eliminating the metabolic cost of aimless zigzagging that can double energy expenditure and accelerate the onset of ketosis-induced fatigue. You reach water sources faster by following solar-aligned drainages that trend predictably downhill, and you establish camp on the correct side of ridgelines before sunset, reducing wind Chill exposure by measurable degrees that separate hypothermia from comfortable rest. Yet the danger escalates dramatically when the sun vanishes behind multi-day cloud cover or polar nights descend during a winter EMP event, erasing your primary daytime reference and forcing an immediate shift to magnetic alternatives that carry their own lethal pitfalls if mishandled. This escalation drives us deeper into the layered redundancy of analog compass work fused with topographic intelligence, where the smallest deviation in declination adjustment can separate rescue from oblivion. Envision pushing through relentless rain in a total communications blackout after a cyber attack downs power grids across entire regions, your compass needle swinging erratically near abandoned vehicles loaded with steel, while flooded trails erase every familiar landmark and 1 degree of uncorrected error sends your group stumbling into a swollen river that has already claimed vehicles and lives in past flash flood events like the 2017 Houston deluge. Analysis shows magnetic navigation depends on the planet's dipolar field lines, which vary in strength and inclination by latitude, requiring constant compensation for deviation caused by local ferromagnetic materials, everything from belt buckles to rifle barrels, that can deflect the needle by 5 to 30 degrees without warning. Common misunderstandings portray the compass as an infallible point and go tool, yet neglect magnetic declination, the angular difference between magnetic north and true north that changes by up to 1 degree every 3 years and reaches 20 degrees in parts of North America, leading survivors to walk parallel to intended roads instead of intersecting them. Many also ignore inclination, the downward tilt of the needle in northern latitudes that causes it to drag on the capsule bottom unless the compass is calibrated for your hemisphere, creating false readings that feel intuitively correct until miles of error accumulate. The hidden science here centers on isogonic charts and deviation tables, where you pre-calculate your area's annual declination shift using printed government maps and apply it as a simple addition or subtraction to every bearing, while employing the center-hold technique that locks the compass to your body axis and eliminates parallax errors inherent in sighting methods. This mirrors inertial guidance principles used in early ICBMs, translating magnetic flux density into reliable azimuths even when solar or stellar cues are unavailable. Supporting evidence appears in after-action reviews from the 2003 Iraq conflict, where special operations teams in urban GPS-jammed environments maintained navigation integrity using lensatic compasses adjusted for local declination, achieving rendezvous accuracy within 200 meters over 20-kilometer night movements, and mirrored in civilian accounts from the 2021 Pacific Northwest heat dome blackouts, where groups used declination-corrected bearings to reach community aid stations while others wandered for days. Survival implications cut straight to the heart of prolonged bug-outs. Precise compass work lets you intersect linear features like power line rights of way or rivers at exact predetermined angles, turning potential starvation marches into efficient resupply vectors and preserving the psychological edge of knowing your exact position relative to safety rather than guessing amid the fog of collapse. Escalation surges when local magnetic anomalies spike near ore deposits or lightning struck trees during thunderstorms that often accompany major solar events, rendering even corrected compasses useless and demanding a return to pure map and terrain fusion that reveals the landscape itself as the ultimate infallible reference. This transition pulls us into the advanced discipline of resection and intersection, where you locate yourself on a paper map by sighting distant peaks and ridges with nothing more than a straightedge and your own eyes. Picture standing on an exposed ridge as night falls in a nationwide grid. Down scenario, distant city glows extinguished forever, and without GPS your only hope lies in identifying 3 prominent terrain features whose bearings you plot on a waterproof topographic quad sheet, yet one misidentified spur ridge, and the plotted lines form a triangle of error large enough to place you miles from your intended water cache, condemning you to another night without hydration in temperatures dropping 20 degrees. Analysis of topographic navigation rests on the universal language of contour lines, each representing a fixed vertical interval that encodes slope steepness, drainage patterns, and hidden saddles invisible from ground level, allowing mental construction of a three-dimensional model accurate to within meters when properly interpreted. The persistent misunderstanding equates map reading with simple line following, overlooking how scale distortion on small-scale maps compresses distances and how relief shading can hide subtle re-entrants that funnel flash floods directly into your path. Novices frequently ignore the map's marginal declination diagram and UTM grid ticks, treating latitude-longitude lines as sufficient when in reality the projection used, usually UTM or state plane, introduces measurable convergence angles that must be factored for long traverses. Hidden within every folded topo sheet lies the science of photogrammetric contour generation, where stereo aerial photography measures parallax to derive elevation data accurate to half a contour interval, combined with the mathematical intersection of azimuths from resection that solves for position using the law of sines in a plane triangle formed by your observed bearings. You improvise the straightedge with a knife blade or credit card edge, and the protractor with the compass bezel itself, achieving fixes that rival modern survey-grade equipment. Evidence from the 2010 Haiti earthquake response demonstrates how search teams using only pre-event topo maps and resection located trapped survivors under rubble by triangulating from visible ridgelines, reducing search times by 70% compared to random grid sweeps, while U.S. Forest Service training statistics show that properly trained individuals maintain positional accuracy within 100 meters over 10 kilometers of broken terrain using nothing but map, compass, and visual association. In the unforgiving calculus of SHTF navigation, this capability means you can plot micro routes that skirt unstable slopes, intersect hidden springs marked only by converging contour fingers, and rendezvous with allied groups at exact grid coordinates agreed upon weeks earlier, turning scattered survivors into a coordinated network that multiplies resources and defense options exponentially. Yet as darkness fully claims the sky and clouds swallow the remaining stars, the final escalation arrives in the form of zero visibility movement where even map and compass fail without a tactile or auditory anchor, compelling the integration of pace counting with micro-terrain feel to maintain course through featureless swamps or urban debris fields. This convergence of all previous layers forms the ultimate forbidden navigation system that no blackout can fully defeat.